So, okay, in this last video, we want to provide a proof for this third and the last property, which tells us indeed like, even though the R function field, that is a subfield of an minus 1, they might not be the same. And indeed, the index as a subgroup is determined by this quantity. As a consequence, we will see that the determinant is this index times the square root of n. And the proof is tricky, and it goes as following. The first thing we can conclude it by using the lattice properties. Please watch out this. This index is finite because an minus 1 and lambda p have the same rank. And now we will define two sublattices of an minus 1 and zn. Let me denote them by b and c. They are again integer lattices, so the coordinates are integers. And for the first lattice, we have the property that each coordinate is 0 in modulo d. Here, di denotes degree of pi's, and sum of the coordinates are 0. So because of this property, we can see that B is a sublattice of an minus 1. And the second lattice we will consider is that is again an integer lattice. Where the coordinates are 0 in modulo di. So indeed B is a subset of C, right? And first thing, like as a first step, what we will conclude is this is also sublattice of an minus 1, by the way, by the definition of an minus 1. And actually no, so this is a subset of z to the n. And the first thing we will calculate is the index of B inside of an minus 1. And but here we also use the second isomorphism theorem. Actually, we use the second isomorphism theorem. Actually, isomorphism theorems for the vector spaces, but these isomorphism theorems hold for groups, ring, modules as well. So indeed, this index so the cardinality, the order of this quotient group can be determined by the quotient an over an minus 1 intersection with C. And by the second isomorphism theorem, we can see that this order indeed an minus plus C, here plus denoted like the sum in our module structure over C. This is something we will also elaborate in the discussion sessions in Zoom, but please also think about it. And actually why we can write these equalities, because by this introduction, we can see that B is indeed equal to an minus 1 intersection C. And since we have also the inclusion as C is a submodule of an minus 1 plus C, and both of them is a subset of z to the n, the index of C in Z is equal to product of the di's just by the setting of C. And here what we want to focus is the computing the index of an minus 1 plus C inside of z to the n. So here the trick is going through defining a homomorphism from z to the n to z modulo kz. Here k denote the greatest common divisor of the degrees of the places we fix in the beginning. And we define this homomorphism by mapping the integer tuples to sum of the coordinates in modulo k. So this is a group homomorphism. And you can easily verify that. And the kernel of, let's say, claim I, and the kernel of this map is equal to an minus 1 plus c. And indeed, it will be useful to compute, computing the index of an minus 1 plus c inside of z to the n. And actually, clearly, like what you can show is that, first, let's see this inclusion. An minus 1 obviously lies in the kernel of this map. And we also need to say that C also should be a subset of this kernel of this map. So to be able to see that, let me consider an element in C. Then by the definition of C, we know that their coordinates are 0 in modulo di. So if they are 0 in the modulo of di, so they should be also 0 in the modulo of the all, like the greatest common divisor of all the i's. And if we take the sum, so it's still 0 in the modulo k, and this shows that C lies in the kernel of this map. So since each of them is a subset of kernel, then sum is a subset of this kernel of this map. And conversely, let me consider an n tuple, like an integer tuple, and we want to see the other inclusion. Such that its image is on the kernel. Let me consider an n tuple which lies in the kernel. Then, by using the basic arithmetic, we know that this sum is equal to r times k for some integer r, and this sum is equal to, like, by using the Bezo identity for the greatest common divisor, by Bezo's identity, this greatest common divisor can be written as a integer combinations of the i's. So we can view the sum of the coordinates in terms of these terms, where the sum coming from the Bezo identity for some S1 up to Sn is Z, and where K is the greatest common divisor of D1 up to Dn. So that means the element we consider in the kernel can be written as, like, just by considering this last equation, can be written as x1 minus r s1 d1, xn minus r sn dn, plus Rs1 D1 up to Rsn Dn. And by using the definition of the elements inside of An minus 1 and C, we can say that these are the vectors in An minus 1 and C. Therefore, we can see the equality for the kernel of this group homomorphism. And by the way, we can also note that this map is onto, so for n element, we can find such an n tuple by the first isomorphism theorem. This is a simple homework to check. And by the first isomorphism theorem, we know that the domain quotient of the kernel is isomorphic to its image, which is exactly the K. So here, so what we have, let me denote this equality by 3. And let me denote the quotient Zn modulo the index of C in Zn, which were the product of the degrees of the places. And we observed that the degree of index of B in An minus 1 was exactly An minus 1 plus C quotient C. And by using these 3 equalities, we can obtain the index of, we can write down this index as the ratio of the product of the degrees over K. So this is the first thing we want to compute. And as a second step, let me say this is step 1. And in the step 2, we want to show that like this 80 in that the index of our function field that is inside of B. And what we want to show that in this quantity divides the class number. And for this purpose, we will consider a nice group homomorphism, which is defined from the lattice B to the class 0 group. And we will define this homomorphism by mapping the vectors in B to the combination of x1 over d1 p1, xn over dn pn plus principal f. So here what you need to observe is that, so this is a degree 0 divisor. And this is a group homomorphism. And we will discuss it in the discussion session. And in this case, again, we compute its kernel. So the kernel contains the n tuples in B, such that this divisor is the principal divisor, because principal, like the set of the principal divisor is the identity of this quotient group. So if this is the principal divisor, there should be a non-zero function. Indeed, this function is in OP
star, right? Because I mean, it has the supports in the fixed set of places, in the n tuples of pi's. And this is indeed the image of, like it can be seen the image of any function in OP star, because when you look at the definition, like when you look at the image of such principal divisors under Pi, what you can see is like the valuation of P, degree of P1 over degree P1. So this is why we have the one-to-one correspondence, and this is indeed all the set of vectors in the function field lattices. So again, by the first isomorphism theorem, we can see that like the quotient, the function field lattice is inside of, is a subgroup of the class 0 group. So that means this quotient group. So if it is subgroup by the group theory, we can say that this index indeed divides the order of this class 0 group. So this is why if we set H0 as the index of the function field lattice delta P inside of P, then by the group theory, H0 divided H. So it can be kind of nice research question, like can we compute explicitly this H0? So I still don't know the answer, but it's definitely worth to investigate it, because it can, it will definitely give us explicit computation for the determinant. And indeed, by using the equality an minus 1b over k, we can denote the index of our function field that is inside of an minus 1 as the product of the index of b inside of an minus 1 times the index of the function field, which is delta p inside of b. And by these computations, we can write down this index explicitly in terms of the product of the degrees we fix over their greatest common divisor times H0. And actually, the last property is like the meaning of the determinant and the meaning of the index. By the lattice theory, we can see that the determinant of a lattice is if our lattice is a subspace of any lattice. In this case, we can complete the determinant of the sublattice in terms of the determinant of the lattice, which contains our sublattice times their indexes. So here, like maybe what you need to pay attention, for instance, for the lattice, if we have kind of this structure, the sublattice will be like this. So the fundamental region or the volume of the fundamental parallelotope will be larger in this case. So this is why the determinant of the sublattice is larger than the lattice which contains the original lattice. This holds for the function field less than the an minus 1. And by the example of an minus 1, we computed its determinant as the square root of n. And by the item 2, we know this index is equal to the product of the degrees of the places over K times H0. So this is why the determinant of the function field can be represented like this. But here's the tricky part to compute this H0, and this is related to compute the index of the function field inside of B. So this is why this computation is some sense important. So tomorrow we will go over these notions over the rational function field. So lattice construction from the rational function fields. And I will explain why lattice constructions from the elliptic function fields are well-rounded and what we can say about the lattice constructions for hyperelliptic function fields. So you can watch the videos by taking your time, and please don't hesitate to contact me as you have any questions. See you tomorrow. Bye-bye.